All right, this next unit is on capacitance, and this video right here is just on the basics of capacitance. So we talk about a capacitor having capacitance, and a capacitor is something that you put in a circuit to store charge or to store energy. So you'll get a chance to do some labs with capacitors in a bit. Okay, a capacitor is any two conductors that are separated by an insulator. The insulator could even just be a vacuum. They form a capacitor. So whenever you have a conductor and then an insulator and then another conductor and the charge isn't allowed to go from the one to the other, we say we have a capacitor. The definition of capacitance then is going to be just how much charge you have on each of the conductors divided by the voltage between the conductors. Okay, so in this unit and for this course, the charge on each what we're going to do is we're going to take charge off of the one conductor and put it on the other conductor. So if we have a conductor here and another conductor here, this will be air. When we take charge off of this one and we put it on that, if we take electrons from here and put them there, then this is going to gain a positive charge and this will gain a negative charge, but they'll be the same value in magnitude. So if we put 100 electrons, we take them from here and put them onto there, then this will have the same magnitude of charge as that. Okay, so capacitance C is equal to Q, where Q is the magnitude of charge on just one of the plates. Just one of these plates. You don't add them both, but just one. Divided by the voltage between these two. So divided by how much, if you do your path integral from here to there, the voltage that you get will be what you divide by. One other thing about this then is that if we want to know what the units are for capacitance, they're going to be coulombs over volts. So coulombs over volts is the unit for capacitance. A farad is what we designate that as. So a farad, 1 farad, we will designate it with an F, is the same thing as 1 coulomb per volt. Okay, we're going to take a look at a special type of capacitor, the most simple type of capacitor, called the parallel plate capacitor. And so that is going to look like this. Now I've drawn this in 2 dimensions, but it's really, this is a plate, maybe a square plate and another square plate. It's got an area. So if my hands were metal, but they were plates, they would look like that maybe. And they're separated by a distance d. Okay, there is an electric field in here. So the electric field looks like this. The electric field is uniform, and it looks like this. Fringes a little bit at the edges. Okay, so that electric field we're going to call E. Put a vector sign over it, I suppose. All right, now with this type of a capacitor, if we use our definition for capacitance, C equals Q over V, then the voltage across this capacitor, if we charge this up Q, the voltage across that capacitor is, if I do a path integral from here to there, then let's just remind you how you get that. The voltage, let's say at A with respect to B, if we put the A there and the B there, it's equal to E dot dr. Okay, here are your drs. You're going from A to B, so there are your little drs, those little paths. And notice they're all in the same direction as E, so you can get rid of the dot product. And then when you do that, because E and D are in the same direction. You can pull the E out of the integral because it's the same at every location. See how the lines aren't getting closer or further apart from each other? So pull that out, and when you do that, you're going to just E, and the integral is telling you to sum up all the DRs, so that's going to be D. So remember, the voltage across parallel plates is ED. So I'm going to put that down here. So the voltage is ED. Okay, now, but the electric field for plates, if you remember, the electric field outside of a conductor, we derived this with Gauss's law. Just outside of a conductor is sigma over epsilon naught. Some of you who had the slab, the electric field due to a slab, you derived this. And so what I'm going to do is I'm going to take that and substitute that in for E. So the capacitance is Q over E. Now E is sigma over epsilon naught. That's the E times D. Okay, but sigma is Q over A. It's the charge per area on this thing. So let me bring the epsilon naught all the way up, and for sigma I'm going to put Q over A. So bring the epsilon naught all the way up, and then sigma is just the charge per area. Okay, we can cancel out a Q, and that A can come all the way up to the top. So the capacitance for a parallel capacitor, parallel plate capacitor, is going to be this. Now don't try and use this for every capacitor. This is only for parallel plate capacitors. That's what that's for, parallel plate capacitors. Okay. So it's just saying that if you want to make a capacitor that has a parallel plate capacitor that has a big capacitance, then here are your two options. You can make the plates really large. That way the capacitance, it will just have more capacitance, more ability to store charge. Capacitance is the ability to store charge. And so if you make the plates really big, you make the capacitance bigger. Now the D, apparently if we get the plates closer together, so if they're this far apart and I get them closer together, somehow that increases the capacitance. Let me explain why. Okay. So I want to give you a conceptual reason for why the A is on top and the D is on the bottom of this formula. But to do that, I think I'm going to go to a second video. So we'll do one more video on capacitance basics. All right, see you there.